Dear students, in this video I am going to take this example and three theorems. Yesterday we have taken this example, but now I want to explain again further. Show that 0 is a limit point of the sequence 1 by n. Fine. Now, for any given epsilon, you can easily find out a number m belongs to n such that 1 by m is less than epsilon. For example, if you take epsilon is 0.5, then you can easily find out this number, say 3, 1 by 3, 0.33, which is less than 0.5, and so on. So for given epsilon, you can easily find out this number, which is this. Fine. Now let us take that n is greater than equals to m. For any n greater than equals to m, if you take the reciprocal number, then 1 by n is less than equal to 1 by m. But as per our assumption, 1 by m is less than epsilon, and we know that n is a natural number which is obviously greater than 0. So this inequality again. So this is the case. So here 0 is less than epsilon, and in between this we are having this number which is of this kind 1 by n. So 0 is less than 1 by n, this which is less than epsilon, and since 0 is obviously greater than minus epsilon, so we can say that this number is laying in between minus epsilon and epsilon. So this is nothing but the neighborhood of 0, because here is this 0, here is minus epsilon, here is positive epsilon. So this is actually the neighborhood of 0. So every neighborhood of 0 contains infinitely many terms for all n greater than equals to 1, and that's why 0 is nothing but a limit point of this sequence, because neighborhood of 0 contains infinitely many terms of the type 1 by n, which is nothing but the term of the sequence 1 by n, and that's why this is a limit point. Fine. So this is the basic definition. Now we will prove some theorems. So first theorem is, if L is a limit point of the range of a sequence an, then L is a limit point of the sequence. First understood the statement. Statement can be understood by the example. Suppose an is this sequence minus 1 raised to the power n. Fine. If you draw this, so here is 1, here is 2, here is 3, here is 4, here is 5. So minus 1 and positive 1. So minus 1, positive 1, minus 1, positive 1, minus 1, positive 1. So this is the sequence. This is the sequence. So what is the range? This is actually the range. What is this? This is the domain. So range is nothing but 1 and minus 1. Range is minus 1. However, the sequence is minus 1, 1, minus 1, 1, minus 1, 1, minus 1, 1, and so on. So this is finite. This is infinite set. This is the difference. So what is the statement? Statement says that if L is the limit point of the range of the sequence an, that means this part, if L is the limit point of range of an, then you have to prove that, required to prove that L is the limit point of an. If L is the limit point of this set, then you have to prove that L is the limit point of this sequence. This is the proof. If L is the limit of this range, then you have to prove that this limit point is also be the limit point of the sequence. This is the statement. I think you understood. Let us see the proof. So suppose S be the set of range of the system. That means here, what is S? S is this. S is this. So let S be the set of the range of the sequence an. Since L is the limit point of S, here since L is the limit point of S, which is a set, then by the definition of the limit, if L is the limit point of set S, then every neighborhood of S contains infinitely many elements of S other than L, because L is this is by the definition of the limit point of the set. Fine. So since L is the limit point of S, so every neighborhood of L contains infinitely many elements of S. Fine. But you see, every element of this correspond to a term of the sequence. Every element of range, for example here 1 correspond to 2, 4, 6, because here is 1, 1, 1, 1. So every element of range correspond to a sequence, to a term of the sequence. At least a term will be there. In here we are having, you can see, corresponding to 1, all the even terms correspond to 1. But suppose there is no repetition, then every term of this range set, actually every element of this range set is actually correspond to some terms of the sequence. Fine. So since L is a limit point, every neighborhood of L contains infinitely many elements of S. Fine. And every element of S is nothing but a term of the sequence. That's why L contains infinitely many terms of the sequence, because they are interconnected. Fine. So every neighborhood of L contains infinitely many terms of the sequence, and hence L is a limit point of the sequence. Fine. Since L contains infinitely many elements of S, but every element of S is nothing but a term of the sequence. That's why every neighborhood of L contains infinitely many terms of the sequence, and that's why L is a limit point. This is the only logic. I think you understood. But the converse of the theorem need not be true. That means if there is a limit point of the sequence, then if L is the limit point of sequence, then this does not imply that L is the limit point of range of an. Fine. This is an example. An is 1 plus minus 1 raised to the power n. What is the sequence? Sequence is 0 and 2. For all the odd terms we are getting 0. For all the even terms we are getting 2. So that's why range set is a finite set. And we know that every finite set has no limit point. Because what is the set? Set is 0 and 2. If you take any neighborhood of this neighborhood contains infinitely many, but here we have only one element, only single element 2. So that's why this is not a limit point. Similarly here, if you take any neighborhood, this contains only 1 point, 0 itself, and hence this is not a limit point. So not a limit point. However, if you draw the sequence, here is 0, here is 2. So here we have 1, 2, 3, 4, 5 and so on. So you will see that by the definition all the odd terms correspond to 0. So 0, 0, 0. But all the even terms are here. This. So if you take any neighborhood of this, any neighborhood of this, then this contains infinitely many terms of the sequence. Fine. So that's why 2 is a limit point of the sequence. 2 is a limit point of the sequence because all the even terms are laying in this neighborhood. Similarly, if you take the 0, just take the neighborhood of this, then all the odd terms will be here, which are infinite, and hence 0 is a limit point of the sequence. Fine. So here this is the counter example. Now the second theorem. Second theorem says that if a sequence an converges to L, then L is the only limit point of the sequence. So first, what is given to you? Sequence converges to L. Then you have to prove that L is the limit point. Then you have to show the uniqueness. So this will be divided into two parts. So first, the sequence an converges to L. Then by the definition, for a given epsilon, there exists a positive integer m such that an minus L is less than epsilon for all n greater than equals to m. Now open this. So we get this L minus epsilon less than an is less than L plus epsilon for all n greater than equals to m. That means an belongs to this interval L minus epsilon to L plus epsilon for infinitely many values because n is greater than equals to m. So if you take any m, then there are infinitely many values of n for which an belongs to this. That's why L is a limit point of the sequence, because this neighborhood contains infinitely many terms of the sequence of the type an, and hence L is the limit point of the sequence. Now we will prove the uniqueness. Of L. Suppose there is another limit point of the sequence, say L dash. So if possible, let L dash be another limit point of the sequence an. Fine. So obviously this is any other limit point. So here is the case. Suppose L is this, L dash is this. This is the limit and limit point also. Both are satisfied here. So now divide this into three parts, 1 and 2, and consider this distance as epsilon from here to here, here to here, here to here. So let L is greater than L dash. Then epsilon can be selected as magnitude of L minus L dash by 3. But since this is possible, so this is nothing but L minus L dash by 3. So now construct the neighborhoods, this and this. Fine. So we are having two neighborhoods. So these are written here. One is this number is L dash minus epsilon to L dash plus epsilon. This number is L minus epsilon to L plus epsilon. Fine. Now here, by the definition, you will see here this sequence, this equation, for all n greater than equals to m, an is laying in this interval. That means here all the terms are laying. An minus L is less than epsilon for all n greater than equals to m. That means all the terms of the sequence is laying here, or you can understand this is here also. For example, this is L, this is say L dash, then here is the band, this is L minus epsilon to L plus epsilon, this is L dash plus epsilon, L dash minus epsilon. This is the band. Fine. So here is M. So we are taking this band. This is L. So all the terms are laying here. All the terms for n greater than equals to m, they are laying here because L is the limit. So how many terms are there possibly? So possibly in this region possibly only n from 1 to m minus 1. They will lay here. They may be here or they may be here, but maximum possible terms they should be lying here. a1, a2 to am minus 1. Maximum possible. Fine. So that means this neighborhood contains maximum possible a1, a2 up to am minus 1. Up to am minus 1 terms here. So this is written here. So at the most 1 to m minus 1 laying here, because this intersection is phi. Because this intersection is phi, there is no limit point here. All the terms either laying here or laying here. There is no point here. Why? Because this is a limit point, this is a limit point. This is a limit point, this is a limit point, and we have selected epsilon in such a way that. So that's why. Fine. So all the terms are laying here. That's why this is a limit point. We have already proved. And but in this neighborhood of L dash, we are having only finitely many terms. So an belongs to this for at the most this, which is a finite term, and that which is a finite number of terms, and hence L dash is not a limit point of the sequence. So this is the proof of this theorem. And in the next video I am going to prove the Bolzano-Weierstrass theorem for the sequences. Fine. So Bolzano-Weierstrass theorem I am proving in the next video. Thank you.